Hello my dear students, welcome to Learning Chemistry is Easy and Fun. The topic that we are now taking up is intermolecular forces, and as the name indicates, we shall be talking about forces between molecules. Now when we use the term molecules, we shall also include atoms as well, because here molecules in general means the species which are present, like atoms, molecules, and a small mention of ions. We shall not be talking about ionic or covalent bond, because ionic or covalent bonds involve, yes, they involve transfer or sharing of electrons. When we are talking about forces, it simply involves interaction between stable species like atoms or between molecules. Between two atoms or between two molecules which are very stable in themselves. These molecules may be homo or heteroatomic. Homoatomic means made up of the same type of atoms. Heteroatomic means made up of the atoms of different types. So homo or heteroatomic. For example, oxygen is homoatomic, made up of the atoms of O only. Heteroatomic like HCl, made up of the atoms of hydrogen and chlorine. Here I've used the term forces. What type of forces can exist between atoms and molecules? So if I take two atoms, there is the nucleus in the middle which is positively charged because of the presence of positively charged protons. The electrons I am indicating outside the nucleus. Same way, for the other atom, we have the nucleus which is positive and the electrons which are present outside. I know the electrons are present in the orbitals and they have different shapes, but for the sake of simplicity, to make our understanding more easy, we are representing them by simple circle diagrams. Now, between the positive and the positive, what type of forces do you think will exist? Yes, between the positive and the positive, there will be repulsive forces, right? They are similarly charged. They have the same charge on them. Between the electrons and the electrons, what type of forces? Again, repulsive forces, because they have the same charge. What about between the nucleus and the electrons? Oh yes, they will love each other, right? Opposite charges in nature attract each other. The nucleus and the electrons, yes, opposite charges in nature attract each other. So when we talk about two atoms or two molecules, or an atom and a molecule, there can be attractive, there can be repulsive forces. In this particular heading, we are talking about the attractive forces that can develop between different species. A short mention here I am making is of ion-dipole interactions. We cannot overlook these interactions because these are very, very interesting and very useful type of interactions. I am not saying that the others are not useful, but this is something that you encounter in your daily life. You dissolve salt in water, right? This is an example of ion-dipole interaction. How is it ion-dipole interaction is what we are going to discuss. The other sets of forces we will be talking about are covered under the blanket name of Vander Waals forces. Henceforth, I will refer to them as the VW forces, right? The Vander Waals forces are classified as dipole-dipole interactions dipole-induced dipole interactions and instantaneous dipole-induced dipole interactions. The first ones are also called as Waals forces. The second one are the Debye forces. The third one are also called as the London forces. Sometimes it is the London forces which are also called as Vander Waals forces. Don't get confused. We will be, as long as you understand the concept, it should be good enough for you, right? So are we ready to go on with the ion dipole interactions? Yes, you are ready? Without pen and paper in your hand? That won't be fun because you will be just mutely watching this video, or maybe after another 10 seconds you'll hop on to another video without understanding the content. So my request and earnest request for you is to pause the video and fetch a pen and paper so that you can write down whatever I am listing over here, and those become your notes. And as I always say, whatever is handwritten remains embedded in the mind for a longer time. In fact, some of you may find that you wouldn't even feel the need to revise this topic if you have understood clearly. So rush off and get a pen and paper so that we can continue with the topic. Ion dipole interactions. We are going to study this in detail now. First of all, before I go ahead with ion dipole interactions, let me touch base on simple, first of all, covalent bond formed by the sharing of electrons between two atoms. Taken two examples over here. Hydrogen, atomic number 1, electronic configuration 1s1, formed by the sharing of a pair of electrons between the two hydrogen atoms. This is also an example of a homoatomic molecule. Hydrogen and chlorine. Again, hydrogen atomic number 1, chlorine atomic number 17. So you have 1s2, 2s2, 2p6, 3s2, 3p5. That will be our electronic configuration for chlorine. So both of them need one electron to pair up. So this type of bond is also formed by the sharing of an electron pair between hydrogen and chlorine. And this also becomes an example of a heteroatomic molecule. Here both the hydrogen are of the same level, right? So they are friends of the same level. There is nobody who is more bossy than the other. So they form what we call as a non-polar covalent bond, wherein the shared pair of electron belongs equally to both the atoms which are involved in bond formation, right? On the other hand, or the word that we use is, both the atoms are equally electronegative. If you are unsure about this term and about this concept, please visit the video on periodic properties, and all these headings are separately covered in detail. Both the hydrogen atoms are equally electronegative, so the shared pair of electron belongs to both of them. In the case of hydrogen and chlorine undergoing single covalent bond formation, chlorine is more electronegative compared to hydrogen. So what it does is, it pulls the shared pair of electron towards itself. So we will have hydrogen, chlorine. This is how we represent the single covalent bond. Chlorine pulls the shared pair of electron towards itself. With the result, it acquires a partial negative charge, whereas hydrogen acquires a partial positive charge. Please understand that this is not complete transfer. This is a shift towards one of the atoms who is stronger in terms of electronegativity, right? So what will happen over here is this is behaving as a partial ionic compound just because of the electronegativity difference between hydrogen and chlorine. This type of a molecule, which has been formed by covalent bonding but shows partial ionic character, is what we call as a polar covalent compound, right? There's been sharing of electrons, but it shows partial charges. Coming to polar covalent compound further. Now here I have a triatomic molecule, water. The OH bond over here is polar because oxygen is more electronegative than hydrogen. So it pulls the shared pair of electrons towards itself, right? Hydrogen partial positive. Similarly, OH bond, again slight positive, negative, right? Treating each of the OH bonds separately. Now, water, if it was a linear molecule, that means if it was like this, what would happen is this is the direction and this is the direction. So what will happen? Both the sides are pressing oxygen to the same extent. The two forces would have nullified each other and there would have been no dipole moment. Now you are coming across a new term, dipole moment. Because of this polarity, this becomes a dipole. Di means two. So there is a positive and a negative end to the molecule, right? So water, if it was a linear molecule, then the dipole moment would have been 0. But we know that water has a V shape, or in fact we say that water behaves in such a manner which is indicative that it has a V shape like this. Oxygen at the help and hydrogen and hydrogen. Dipole moments are directional. This is directional character. With the result, there is a net dipole moment acting in the upward direction. In other words, water has a dipole moment. It behaves as a polar molecule. How does this affect the behavior of water? Let us see in the context of ion dipole interaction. We've got sodium chloride to be dissolved in water. Now sodium chloride is an ionic compound which is formed by the transfer of electrons from sodium to chlorine, right? Water on the other hand is a covalent compound. You have read in chemical bonding, like dissolves like. But we've got an ionic compound which you know by everyday example that easily it dissolves in the covalent compound, that is water. Salt easily dissolves in water. How do we explain this behavior? This is explained on the basis of the polar character of water molecule. Water, because of its dipole, now I can simply represent this water by a small donut long shape, so negative and a positive end, to represent it simply, right? I don't want to go into this complex behavior as of now. So what happens is, basically we are saying that water has a positive and a negative end. The positive end of the water molecule can tug or can pull at the negative end of the sodium chloride structure, whereas the negative end of the water molecule can pull the positive ions in sodium chloride. So what do we have here now? Let us see. Sodium ions surrounded by water molecules. The negative end of the water molecule is facing the sodium ions. It has surrounded it from all sides. So the place which was earlier being occupied by chloride ions. Now why I am saying place? Because you will study it in the solid state. Sodium ion surrounded by the chloride ions. That place is now taken up by water molecules with their negative end facing the sodium ions, right? And that is why the sodium ion now becomes hydrated. What about the chloride now? Oh, even that is not left alone. So we have the chloride ion again surrounded by water molecules, but the positive end of the water molecule will now face the chloride ions, right? You see over here? Now the sodium and the chloride ions have become hydrated, and the forces of attraction between the sodium and the chloride ions are broken. The electrostatic forces of attraction between them are broken, and they become hydrated ions, and they become separated, and sodium chloride dissolves in water. This also goes on to explain why solid sodium chloride is a non-electrolyte. It does not conduct electricity in the solid state because the sodium and the chloride ions are holding each other tightly because of the opposite charges. On the other hand, when you either heat it, so you are providing energy to the ions, or you dissolve it in water, in which case the ions get separated because of the polar nature of water molecule. The ions now are separated and they can be carried away by the electric charge, right? This explains the solubility of ionic compounds in water, the ion-dipole interactions. Of course, these are not covered as part of Vander Waals forces or the intermolecular forces, but I felt the need to explain it in order to justify or explain a very important phenomena that we observe. I hope you have noted this down, because this is going to come in very handy for you when you revise. Please make a note of this, draw this, and try answering the question, why is first sodium chloride a non-electrolyte in the solid state or a non-conductor of electricity in the solid state but becomes an electrolyte? Second, sodium chloride has a high melting point. Third, sodium chloride exists in the solid state. Try answering these questions on the basis of the explanations that I have given over here. Please don't forget the terms electrostatic forces of attraction. Don't forget the terms dipole, polar. These are important terms. And we shall now move on to the next set of forces. Dipole-Dipole interactions. As the name clearly indicates, we are talking about two polar molecules interacting with each other. Now these polar molecules, they can be of the same compound or they can be of the different compound. So I've taken an example over here of HCl and HCl interacting with each other. Chlorine, being more electronegative, pulls the shared pair of electrons towards itself, becomes partially negative charge, whereas hydrogen acquires a partial positive charge. Now this partial sign, we are putting it as this, positive or negative, right? Now, similarly, in the second HCl molecule, the same phenomena takes place. Now what about plus and minus? Yes, They are opposite charges, they will pull each other. Now because of this pull, a force of attraction develops between two molecules of HCl and they will start coming closer to each other. But we know that HCl is a gas. So do these forces of attraction exist even when the molecules are far away from each other? No. The molecules, the strength of these forces is not very high. It's not as strong as the ion dipole interactions. The ion dipole interactions are stronger compared to the dipole-dipole interactions. So what happens is their area of strength or the area within which they will exercise their control will be limited. That is why the molecules need to be brought closer for these forces to show effect. That is why when you try to liquefy HCl, what do? You decrease the temperature, right? And you increase the pressure. Correct? By increasing the pressure and by increasing the pressure, you are bringing the molecules closer to each other. By decreasing the temperature, you are reducing their kinetic energy. With the result, they will come closer to each other. Dipole-dipole interactions will come into play and the molecules of HCl can be liquefied. That means HCl will now exist as a liquid. Similarly, HCl, it's a covalent compound. Water is a covalent compound as well. How does HCl dissolve in water? Positive, negative. We've just now done that hydrogen acquires positive and negative charge over here, right? So negative and positive. The negative tugs at the positive and we have the dipole-dipole interactions which have taken place. So these dipole-dipole interactions, can they exist in a stronger way? Can they increase in strength under circumstances? We are going to do hydrogen bond as a special case of dipole-dipole interactions. But this we will cover in a separate video because this particular topic warrants a separate discussion. So hydrogen bond as a special case of dipole-dipole interactions would be a separate video, right? Have you noted this down? Are we ready to do the next type of forces? Because these become your notes. Dipole-induced dipole interactions, or also called as Debye Forces, is what we are doing next. Do you think I need to explain? Because the name itself speaks. Dipole, that means we have a molecule which has a permanent dipole, and the simplest example that we are taking up here is water. We have already discussed how water, because of its V shape, has a dipole moment, a permanent dipole moment. Now what happens is water comes next to a molecule which is otherwise neutral, relaxed. It's got two atoms which are very friendly with each other at par and they are not bothered about fighting with each other, and water comes and nudges, hey, hello, come, make friends with me. This oxygen says, feels a bit tempted because he's got a negative charge. So what happens over here is the electrons, they, because of their tendency to be in a state of continuous random motion, these electrons, they get pushed away from the negative end of the water molecules, the electrons of the oxygen molecule. So just imagine oxygen molecule that I have drawn over here, a non-polar oxygen molecule. Let me show it, or let me represent it simply by a circle wherein the positive and the negative are living in harmony with each other. Whereas this water molecule comes and spoils that relation, and it has a tendency to push away the electrons and pull or tug towards the nucleus. With the result, this oxygen molecule, which was otherwise non-polar, starts behaving like a polar molecule only in the presence of the molecule which already has a dipole. That is why the word induce. This doesn't have the dipole initially. It is not behaving as a polar molecule. It is only in the presence of a polar molecule that it starts behaving as a polar molecule. And now both of them are dipoles and dipoles. That means molecules with polarity 2 poles. And they start attracting the opposite ends towards each other. Or it could be plus here and a minus here, and vice versa for the 2 charges at the ends. Because of this, the 2 molecules will come closer to each other. They will develop that friendship. Now please remember, these are just forces. These are not overlaps. These are not transfer. This is not sharing. This is temporary closeness of the 2 molecules. A temporary friendship of the 2 molecules. What does this friendship depend on? Of course, water first of all, or we say that the molecule which is causing the polarity, it should have enough dipole moment in order to affect the polarity of the non-polar molecule. So the dipole moment of the polar molecule affects the induced dipole in the affected molecule. And what about the non-polar molecule? Even that should be ready to develop that friendship. What in the terms of chemistry we say polarizability, the ability of the electrons to spread in order to develop that friendship. So the polarizability, ability of the non-polar molecule to get polarized will also affect the strength of this dipole-induced dipole interaction. And this goes on to explain how gases like oxygen, etc. are able to dissolve in water. This is one of the examples that I have taken. Can you give me a few more examples of dipole-induced dipole interactions as to how they affect the behavior of the substances? Look out for examples of this, and also tell me, will these forces be stronger or weaker than the dipole-dipole interactions? One is that you have 2 molecules which are already polar and they come and they shake hands. The other is this one is coming and forcing this one to shake hands. So which one of the 2 would be stronger? Yes, the dipole-dipole interactions are stronger. So now we've got the ion dipole interactions which are the strongest out of the forces that we are talking about. We are not considering the ionic and the covalent bond. We're just talking about the intermolecular forces. Second comes the dipole-dipole interactions, and then of course the dipole-induced dipole. You know, there's another kind of force what we call as the London forces, where it's like none of them has a dipole and all of a sudden they start behaving as polar molecules. Does that also happen? Let's go and see further. Have you noted this down? If you haven't, please make a note of this. and these are the two factors which will affect the dipole-induced dipole interactions, right? And don't forget to give me the examples and write them down in your notes for future reference. Instantaneous dipole, induced dipole interactions. Now, these are also called as London forces. Can you tell me why they are called London forces, or to be more specific, after the name of which scientists are they called London forces? As the name indicates, instantaneous dipole, just like you have instant Maggi, right? Instant noodles. This is a relationship which develops out of need. So what happens is, oh, they are hungry for friendship. So here, each of the molecules, now what I have done over here is I have depicted this kind of interaction in 3 stages. Although it's not that these stages are practically existing, but to explain it, it's easier to understand this way. You also have to remember that the electron is not localized. It's not concentrated at one point. It is all over the place. The electron cloud is moving continuously. Here we've got stage 1, where these two molecules are complete strangers. In their own world, A and B is what I'm going to call them. Now this is completely neutral. Let's say I'm talking about two atoms of the inert gases. Let's say helium, right? So what happens over here is, this is completely satisfied, no need to interact. But the electron cloud in each of these atoms, although they are completely satisfied, is a bit naughty. It keeps moving around in all directions. With the result, there are certain times where the electron cloud is more concentrated at one end of the atom compared to the other times. Because of which one end of this behaves as the negative end and the other becomes the positive end. That is why the term instantaneous dipole. That means it's not originally having a dipole, but for an instant it develops this dipole. Now, because it has developed this dipole, the second atom says, oh, seems to be something fishy. There seems to be somebody calling me from the other end. So the electron cloud of this one attracts the nucleus of the second atom or the molecule. When it attracts the nucleus, what happens is, yes, the atom B also develops a dipole just because of the instantaneous dipole of the first atom or the molecule. Hence the name instantaneous dipole, induced dipole interaction. Originally, both of them are quiet, simple, not bothered about anything, but because of the electron cloud of one, the nucleus of the other gets pulled towards it. As I've given the example, inert gases. Inert gases, when their when their atoms are brought close to each other by reducing the temperature and by increasing the pressure. Now it's not easy to liquefy the inert gases. Why? Because these type of forces are quite weak. They are not very strong. So in order to develop these, and also these type of forces will develop between two molecules or atoms which are in almost like direct contact, which are very close to each other, right? The molecules are in close vicinity. We are given an approximate idea of 500 picometer, right? So they are in the close vicinity of each other. The area of this force of attraction does not extend to a large surface area. It is limited to small vicinity of itself. That is why we need to apply high pressure and very low temperature in order to liquefy gases. Similar is the case with examples like hydrogen, oxygen, nitrogen and so on. Graphite, if you remember, we do Vander Waals forces, right? Sometimes the Vander Waals forces are also studied under the instantaneous dipole induced dipole interactions. I shall be talking about that separately as a Vander Waals force. So again, because of the Vander Waals forces between the different layers of the carbon molecules, what do we have is graphite is soft and slippery. So this can again be attributed to the Vander Waals forces, right? What are the factors which in general affect the strength of the Vander Waals forces is what we are going to do next. Before that, please copy this so that it becomes your perfect. These become your notes. You will not need handouts. Go ahead, copy it. Factors affecting Vander Waals forces. We are doing it for all the forces, all the three types that we have done. The first and most important factor is the atomic mass or the molecular mass. Why atomic mass? Because we just now spoke about the inert gases as well, which show these kind of forces. With increase in molecular mass, what will happen is when the molecular mass or the atomic mass increases, the size of the atom also begins to increase. The atom or the molecule begins to increase. With the result, the dispersal of the charge is more. When the dispersion of this charge is more, the Vander Waals forces will also increase. My arrow up means an increase. So with increase in atomic or molecular mass, because there is an increase in surface area, the Vander Waals forces also increase. They will be spread over a larger area and they will be able to affect to a greater strength. Increase in branching. Now this is a very important point which you will be doing under all the organic compounds that you will study. If you've not done that or if it has not been started as yet in your syllabus, no worries. Here I am taking the example of a simple compound having 5 carbon atoms and 12 hydrogen atoms. It's a pentane. I have taken various structures of the same compound called as isomers. I am not naming them because I don't want to confuse you with the names. Now if you notice 1, 2, 3, 4, 5 carbon, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 hydrogen. The same number of carbon and hydrogen here, the same here. What is different in all these? These are called isomers. The difference is in the arrangement of the carbon atoms. Here there's a 1 branch, here there are 2 branches of the chain. If you notice the boiling points, this is 309, this is 301, this is 282. So what is happening is with increase in branching, the boiling point is actually reducing. Why is it so? When you are increasing the number of branches, the shape which was otherwise linear and the chains could fit into each other easily, they are turning more spherical because the sphere, now in this case they are turning spherical. Now because of this spherical shape, the surface area becomes smaller. When the surface area becomes smaller, the strength of these Vander Waals forces is spread over lesser area. The strength also reduces. So with increase in branching, the strength of the Vander Waals forces will, yes, it will decrease. That is why it is easier to break the bonds between 2 molecules of this compound or C5H12. This is also called as, if you know, can you tell me? This is If it is, you number it, it is 1, 2, 3. So this is 2,2-dimethyl propane. That's its IUPAC name. This is 2-methyl butane. Now both of them have the same number of carbon and hydrogen, but neopentane will have lower boiling point as compared to isopentane. For the simple reason, because we've got more branches over here. Also affecting the Vander Waals forces that we have already discussed is the temperature. With increase in temperature, the Vander Waals forces will, temperature increases, Vander Waals forces will, very good, they will decrease. The fourth factor is the pressure. This also we have discussed. We increase the pressure, Vander Waals forces will also increase. Arrow up and down is, it's easier to relate to. So you can write it in short form so that you can recall the direction of the arrows. Also is the tendency of the molecule to get polarized. So what we also called as polarizability of the atom or the molecule. Right? Now we've covered intermolecular forces step by step. What do you have to do next? Yes, copy it. If you don't understand the meaning of any symbol, just go through the video again and you'll be able to relate to it. We are not yet done because we have to do hydrogen bond as a special case of dipole-dipole interaction. But because it's a very important and a little lengthy heading, we shall be taking it up as a separate lesson. For now, I'm signing off with good wishes for your studies as well as good health. Remain subscribed and share the joy of learning chemistry with friends and classmates.